One point that I want to insist here is the following. This one. What he says, supersynchronous stationary solutions. Either my solution is supersynchronous, either I have a contracting torque. Well, nowadays, some space missions allows to know the rotation of the satellites with big precision. And what we see is that they are synchronous, notwithstanding the fact that they have eccentricities different of zero. So they are trapped not in a supersynchronous rotation, but they are trapped in a synchronous rotation. To accommodate the theory to the fact, people say, okay, but the body has a triaxiality, frozen triaxiality, and because of this frozen triaxiality, we will have a contracting torque that will bring the system to a synchronous situation. Well, the second part I used to call it the syndrome of Dr. Jekyll and Mr. Hyde. So the body is responding to tides, but it's hard enough to keep an initial deformation. Okay, this is not very sympathetic, I have to say. Well, anyway, what I can say is that if I am not seeing that the motions are supersynchronous, this means that something is wrong with the theory. Something is wrong with the theory. It's important that even in the frame of Darwin theory, I can solve this paradox without putting an asymmetry. For instance, this conclusion is done assuming that the rheology is the Darwin rheology, frequencies lags proportional to frequencies. But if, like Efroimsky and Linné, I put lags inversely proportional to frequency, or a power law with a negative frequency power, I can also obtain different results. But anyway, this is not satisfactory, and this is the reason why I will make the first steps of the second part of these lectures. Okay, I have time. And to say that a different theory, a theory different of the theory of Darwin, that has been proposed by myself in 2012. Here is the reference of the theory, but in the last slides I will give a more complete list of references. This is the creep tide theory. What says the creep tide theory? Well, first, there are several recent theories trying to improve our knowledge on the tides, and that are founded and to look at the inelastic tide with models which are not exactly the model used by Darwin. The first one is this one, Efroimsky, Linné, and Williams, that, as I say, have changed the way in which the lags depend on the frequencies, have inverted the law, okay, putting There is a theory by Remus, 2012, that is founded on the old theory that has been proposed by Zahn 50 years ago, and that has some similarity with the creep tide theory that I am showing, but they are more interested in internal processes inside the star, which is not our case. Ogilvy and Lee also, my own, and more recently, Correia, Bouet, Lascar, etc., some papers in 2014 and 16 using a Maxwell body. I will tell you what is a Maxwell body later, as a model for the body. All these theories depart in a larger or lesser extent from Darwin's theory. So let's talk about the creep theory. So first is a new theory, completely different of every theory given before. The aim of this theory, to substitute plugged haddock legs by one physical law. Okay? And which is the physical law? The physical law is this one. Look at this figure. In this figure you have zeta is the actual surface of the body. It's this line here. Okay, this is the actual surface of the body. But this body is not in equilibrium. Okay, the body is not in equilibrium because everything is moving. And the body does not respond to the actions instantaneously. Okay? If the body was responding to the external forces instantaneously, it would be here. This is the surface of instantaneous equilibrium. Virtual, because it's just a surface of equilibrium. The real one is this one. What we say, what is this ansatz? No? Is that this surface, the actual one, will tend towards the virtual one. And will tend, and the surface will tend one to the other, and he will tend with a velocity that is proportional to the difference. So a very simple law. In fact, I was very ashamed to me when I discovered that Newton had already done it for other problems. So, and this is called, this ansatz is called Newtonian Creep. So what happens is this. We have the bodies in this theory behave as fluids, but fluids with a very low Reynolds number. They cannot have turbulence, they cannot have strong effects inside. They adjust the position, you adjust smoothly. So the actual surface of the body is this one in this figure, and this is the equilibrium surface. Okay, this extra weight will make this part come down, and here, how we compute the equilibrium surface? When we compute the equilibrium surface, we use the whole mass below the surface to compute the forces. But there is a mass missing here. So it's like if I had here a negative mass that it makes the weighting over the actual surface, but in the wrong direction, because it's not true. This is not a real force. This is simply I am discounting something that was included in the equation to compute this surface, but that is no longer there because of this wave make a throw in this position. So we can study this problem using using a little bit hydrodynamics, and we may use the Navier-Stokes equation to study the problem which figure I have shown there. And when I do that, I see that this value gamma, this constant of proportionality that appears here, is something that is inversely proportional to the viscosity of the fluid. So now I am assuming that the body is a fluid, okay? The earth is a fluid, and that this fluid has a given viscosity eta, and so I have a relaxation factor that, okay, W is the specific weight at the level of the the surface of the body, r is the radius of the body, and 2 eta. Okay, so this is the relaxation factor. It behaves sometimes like a critical frequency. The dimension is times 2 minus 1, so it is given usually measured with seconds to minus 1. So if we translate what we know about the several celestial bodies, we know how the dissipation, we know several things of the bodies. I can compute the values of gamma. What is interesting to see is that when we consider stiff bodies, like the planetary satellites, the Earth, or the Moon, the value of gamma is 10 to minus 7, 10 to minus 8, 10 to minus 9 seconds to minus 1. In the paper I mentioned, it appears as hertz, but apparently it's wrong to use hertz when the quantity is not a frequency, even if the dimension is the same. Okay, and we can with this value obtain the viscosity of the bodies, and these are the kind of viscosities that we know in laboratory experiments for the constituents of these bodies. But if I go to the big planets, Neptune, Saturn, Jupiter, or the hot Jupiters, or the solar type stars, look, there is a big difference here. There is a big difference here. So here I have okay, look at the time scale. Okay, minus 8, 10 to minus 9, 10 to minus 8, 10 to minus 7. Here I have 10, 10 to 2. So there is a big difference in these quantities when I consider gaseous bodies or when I consider stiff bodies. This is why in this region, happily, Darwin theory works well, but not in that one. The two bodies respond to tidal effects in completely different ways. Okay, I will stop here. Okay, I will let the equations for tomorrow. Have a good lunch.